Hello there, traveler. Before we begin tonight's journey among the stars, take a moment to settle in. How was your day today? I hope it brought you peace, or at least a little light. Let me know in the comments where in the world you're watching from, and what time it is for you right now. I love seeing how far this little space voyage reaches. Now, take a deep breath. Let go of the noise of the day and let your mind drift. If you're new here, feel free to subscribe. There's a whole universe waiting for you. Sleep well and enjoy the story. Alfred Wallace's Lineage and Space, a meditative journey through biogeography. In the quiet depths of night, when the world settles into its ancient rhythms, there exists a story that spans continents and epochs, a tale written not in words, but in the distribution of life itself across the vast canvas of Earth. This is the story of Alfred Russel Wallace, the forgotten architect of evolutionary thought, whose wanderings through distant archipelagos revealed patterns that echo through the cosmos like ripples in a still pond. Wallace walked where Darwin never ventured, through the emerald labyrinths of the Malay archipelago, where tigers prowled on one island while strange marsupials hopped on another, separated by waters no wider than a river, yet divided by evolutionary gulfs deeper than oceans. His observations became the foundation of biogeography, the science that maps life's journey across space and time, revealing how geography shapes the very essence of existence. Tonight, as consciousness drifts towards sleep, imagine these patterns extending beyond our blue marble into the infinite darkness, where distant worlds might harbor their own invisible lines, their own Wallace lines, drawn between alien biomes under foreign stars. The principles that Wallace discovered in earthly archipelagos may someday guide us through the archipelagos of space, where planets drift like islands in the cosmic ocean, each harboring its own unique experiments in the art of being alive. The story unfolds slowly, like evolution itself, beginning with a single man's curiosity and expanding into universal truths that connect the flutter of a butterfly's wing in Borneo to the potential flutter of unknown wings beneath the ice of Europa. In this gentle exploration, the boundaries between Earth and cosmos dissolve, revealing biogeography not as a merely terrestrial science, but as a lens through which to understand life's potential throughout the universe. The Naturalist's Awakening. In the year 1848, when the world was smaller and its mysteries deeper, a young man named Alfred Russel Wallace departed England's grey shores with nothing but curiosity and a collector's net. The Amazon called to him first, that vast green lung of the planet where rivers snake through endless forests like arteries, through some sleeping giant's body. For 4 years, he wandered through this cathedral of leaves, watching how species changed as he moved from river to river, from highland to lowland, from the edge of one ecosystem to the heart of another. The Amazon taught Wallace that nature was not uniform, not a single garden tended by a divine gardener, but a mosaic of countless experiments, each piece shaped by the unique conditions of its place. He collected over 8,000 specimens, each one a word in the language of life, each one telling a story of adaptation to specific circumstances. The butterflies that danced through the canopy were not the same as those that fluttered near the forest floor. The birds that sang in the morning mist were different from those that called at twilight. Each niche, each micro-habitat, each fragment of the vast Amazon had shaped its inhabitants into forms found nowhere else on Earth. But the Amazon was merely the prologue to Wallace's true revelation. In 1854, after losing most of his collections in a ship fire that consumed years of work in mere hours, Wallace set sail again, this time toward the scattered jewels of the Malay archipelago. Here, among islands that dotted the tropical seas like stars scattered across the night sky, he would discover patterns that would revolutionize humanity's understanding of life's distribution across the planet. The archipelago stretched across thousands of miles, from Sumatra in the west to New Guinea in the east, a chain of volcanic emeralds rising from azure depths. Each island was a world unto itself, separated from its neighbors by waters that seemed narrow on maps but vast in their biological significance. On some islands, Wallace found tigers, elephants, and other creatures familiar from Asian mainlands. On others, he encountered marsupials, birds of paradise, and forms of life that seemed to belong to a different planet entirely. As Wallace moved from island to island, collecting specimens and noting their distributions, he began to perceive an invisible line running through the archipelago, a boundary more significant than any political border. To the west of this line lay the biological realm of Asia, with its placental mammals and familiar bird families. To the east lay something entirely different, a biological realm more closely related to Australia, dominated by marsupials and unique bird lineages that had evolved in isolation for millions of years. This line, later named the Wallace Line in his honor, became one of the most important discoveries in the history of biology. It revealed that geography was not merely the stage upon which life performed, but an active participant in the drama of evolution. The narrow straits between islands had acted as filters, allowing some species to cross while barring others. Ocean currents, wind patterns, and the depths of underwater channels had all played roles in determining which forms of life could colonize which islands. Wallace's insight extended beyond mere observation. He began to understand that the history of life was inseparable from the history of the Earth itself. The rise and fall of sea levels, the drift of continents, the formation of mountain ranges, and the opening of ocean basins had all left their marks on the distribution of species. Life and landscape were partners in an ancient dance, each shaping the other across the vast expanses of geological time. Titian. Now, close your eyes and picture how all of this might look from above. Imagine the Malay archipelago as it appeared millions of years ago, when sea levels were lower and land bridges connected islands that are now separated by water. See the slow procession of ice ages, the gradual rise of oceans, the patient work of time carving channels between lands. Watch as species migrate across these changing landscapes, following the slow rhythm of climate and geography, adapting to new homes while leaving traces of their origins in their genes and their forms. The architecture of isolation. The islands of the Malay archipelago became Wallace's laboratory, each one a natural experiment in the relationship between space and life. On Borneo, the largest island in the region, Wallace found vast forests that seemed almost infinite in their diversity. Here, orangutans swung through the canopy, alongside proboscis monkeys, while sun bears prowled the forest floor and rhinoceros hornbills announced the dawn with their prehistoric calls. The biological richness was overwhelming, a testament to the creative power of evolution when given vast spaces and deep time. But as Wallace moved eastward across the archipelago, he noticed something remarkable. The islands became smaller, and with their diminishing size came a corresponding decrease in the number of species. This was not merely a function of habitat area, though that played a role. It was something more fundamental. a relationship between isolation and biological diversity that would later become known as the island biogeography effect. On the smallest islands, Wallace found ecosystems stripped to their essentials. A few species of birds, perhaps a single type of bat, maybe a lizard or two. These creatures had somehow managed to cross the water barriers that surrounded their island homes, and once there, they had often evolved into forms found nowhere else on Earth. The isolation that limited the number of species that could reach these islands also provided opportunities for those that did arrive to diversify and adapt in unique ways. This pattern of isolation and diversification became one of Wallace's most profound insights. He realized that geographic barriers were not merely obstacles to be overcome, but creative forces that shaped the very nature of life. A mountain range could split a single species into two populations, each adapting to the conditions on its side of the barrier. Over time, these populations might become so different that they could no longer interbreed, creating two species where once there had been one. The process was slow, measured in thousands or millions of years, but its effects were visible everywhere Wallace looked. The bird of paradise species that adorned the islands of New Guinea each occupied their own territories, their brilliant plumage and elaborate courtship displays having evolved in isolation from one another. The marsupial mammals of the eastern islands showed similar patterns, with different species adapted to different ecological niches and geographic regions. Wallace began to understand that the Earth's surface was not a uniform stage for life, but a complex mosaic of barriers and bridges, filters, and corridors. Ocean currents could carry seeds and small animals across vast distances, while mountain ranges and deserts could isolate populations living only miles apart. Climate zones created invisible boundaries, with tropical species unable to survive in temperate regions, and Arctic species unable to tolerate the heat of lower latitudes. These patterns of distribution told stories of deep time, of continents that had drifted across the face of the planet over millions of years, carrying their biological cargo with them. The similarities between the animals of South America and Africa, the unique flora of Australia, the distinctive fauna of Madagascar, all these patterns made sense when viewed through the lens of biogeography as chapters in a vast book written by the movement of land and sea across geological time. Wallace's work in the Malay archipelago revealed that every species was a product not just of its immediate environment, but of the entire history of its homeland. The ancestors of every creature he collected had been shaped by ancient climates, by the rise and fall of sea levels, by the collision of continents and the opening of ocean basins. Each species carried within its genes and its form the memory of countless geographic events, a biological record of the Earth's changing face. The implications of these discoveries extended far beyond the islands where Wallace made his observations. If life on Earth was so profoundly shaped by geography, then life elsewhere in the universe might be similarly influenced by the unique geographic features of its home worlds. The principles of biogeography might become principles of astrobiogeography, helping future explorers understand how life might be distributed across the varied landscapes of distant planets. The invisible boundaries. As Wallace continued his explorations, he began to map the invisible boundaries that divided the living world. The Wallace Line was only the most famous of these barriers, but the archipelago revealed many others, each one a testament to the power of geography to shape the course of evolution. Some barriers were obvious, broad stretches of ocean that few land animals could cross. Others were subtle, like changes in water temperature or salinity that prevented marine species from dispersing. The most profound barriers were those created by time itself. Wallace realized that the current distribution of species was not a snapshot of a static world, but a moment in an ongoing story of change. The ice ages had repeatedly reshaped the planet's climate, causing sea levels to rise and fall, forests to expand and contract, and species to migrate vast distances in search of suitable habitat. Each glacial cycle had redrawn the map of life, creating new opportunities for some species while driving others to extinction. During the Ice Ages, what is now the Malay Archipelago looked very different. Lower sea levels had exposed vast areas of shallow sea floor, creating land bridges between islands that are now separated by water. These bridges allowed Asian species to colonize islands that they cannot reach today, while the subsequent rise in sea levels trapped populations on islands where they evolved in isolation. The result was a complex pattern of distribution that reflected not just present geography, but the ghost of ancient landscapes. Wallace began to understand that every species was a temporal, as well as a spatial refugee, carrying within its genes the memory of climates and landscapes that no longer existed. The tropical species of the archipelago had ancestors that had survived ice ages in refuge areas, small pockets of suitable habitat that persisted even when most of the region was cooler and drier. These refuges had served as evolutionary workshops, places where species could persist and adapt until changing conditions allowed them to spread again. The concept of refuges became central to Wallace's understanding of biogeography. He realized that the current distribution of species was like a palimpsest, with layers of history written one over another. The most recent layer showed the effects of current climate and geography, but beneath it lay the traces of older patterns, ghost ranges that revealed where species had lived in the past. This temporal dimension of biogeography added new depth to Wallace's understanding of the relationship between life and landscape. Species were not simply adapted to their current environments, but carried within them the evolutionary legacy of all the environments their ancestors had encountered. A bird species living on a tropical island might have drought-resistant genes inherited from ancestors that had survived in desert refuges during past climate changes. The boundaries between biological realms were not fixed lines, but dynamic zones that had shifted back and forth across the landscape as climates changed. The Wallace Line itself was not a permanent feature, but a temporary manifestation of current sea levels and climate conditions. In the past, it had been in different places, and in the future, it might move again as the planet continued its endless process of change. This dynamic view of biogeography revealed that the distribution of life was not a puzzle to be solved once and for all, but an ongoing story of adaptation and change. Each species was both a product of its current environment and a traveler from deep time, carrying within its genes and its form the record of a journey that had lasted millions of years. Wallace's insights into these invisible boundaries would later prove crucial for understanding how life might be distributed in space. If geography created such complex patterns of distribution on a single planet, what patterns might emerge on worlds with different climates, different ocean patterns, different continental configurations? The principles of biogeography might serve as a guide for exploring the biological geography of other worlds, helping future astrobiologists understand how life might be distributed across the varied landscapes of distant planets. Now, close your eyes and imagine these invisible boundaries extending beyond Earth. Picture how ocean currents on an alien world might create barriers between biological realms, how mountain ranges on distant planets might isolate populations and drive speciation, how ice ages on other worlds might force species into refuge areas where they could evolve in isolation. See how the principles Wallace discovered in earthly archipelagos might apply to the archipelagos of space, where planets drift like islands in the cosmic ocean. The deep time perspective. Wallace's greatest insight was perhaps his recognition that the present distribution of life could only be understood through the lens of deep time. The patterns he observed in the Malay archipelago were not simply the result of current geographic conditions, but the accumulated effects of millions of years of Earth history. Every species carried within its genes and its form the memory of ancient climates, vanished landscapes, and long-extinct relatives. The fossil record revealed glimpses of these ancient worlds. In the rocks of Europe, Wallace found evidence of tropical forests that had once thrived where glaciers now carved valleys. In the caves of England, he discovered the bones of elephants and rhinoceroses that had wandered across landscapes now inhabited by sheep and cattle. These fossils told stories of a planet in constant flux, where climates shifted, continents moved, and species migrated vast distances in response to changing conditions. Wallace began to understand that the Earth's biological history was inseparable from its geological history. The rise of mountain ranges had created new climates and new barriers to migration. The opening of ocean basins had separated continents and isolated their biological communities. The collision of continents had brought together species that had evolved in isolation, creating new opportunities for interaction and competition. The concept of continental drift, not yet accepted in Wallace's time but implicit in his observations, provided a framework for understanding these patterns. If continents moved across the face of the planet, carrying their biological cargo with them, then the similarities between the life of different continents made sense. The marsupials of Australia and South America, the distinctive plants of Africa and South America, the unique animals of Madagascar. All these patterns could be explained by the slow dance of continents across geological time. Wallace's work revealed that biogeography was not just about understanding where species lived, but about understanding how they had come to live there. Every distribution pattern told a story of migration, adaptation, and survival across vast expanses of time. The tropical birds of the Malay archipelago had ancestors that had survived ice ages, crossed ancient land bridges, and adapted to changing sea levels. Their current distribution was the endpoint of a journey that had lasted millions of years. This deep time perspective transformed Wallace's understanding of evolution itself. He realized that natural selection was not just a mechanism for adapting to current conditions, but a process that operated across geological timescales. Species that survived and thrived were those that could adapt not just to their immediate environment, but to the long-term patterns of environmental change. The ability to survive ice ages, to cross geographic barriers, to adapt to new climates. These were the traits that determined which lineages would persist and which would vanish. The implications of this deep time perspective extended far beyond the Earth. If life existed on other worlds, it too would be shaped by the geological history of its home planet. The distribution of life on a planet with a different history of continental drift, climate change, and geological activity would create different patterns of biogeography. Understanding these patterns would require not just knowledge of current conditions, but a deep understanding of planetary history. Wallace's insights into deep time would later prove crucial for astrobiology. The search for life on other worlds would need to consider not just current conditions, but the entire history of planetary environments. A world that seemed inhospitable today might harbor life that had evolved during more favorable periods in its history. Conversely, a world that seemed ideal for life might lack the long-term stability necessary for complex evolution. The deep time perspective also revealed the fragility of current biological patterns. The distributions that Wallace mapped were not permanent features of the planet, but temporary arrangements that would change as the Earth continued its endless process of geological and climatic evolution. Species that seemed secure in their current ranges might face extinction as climate shifted and barriers moved. New opportunities would arise as land bridges emerged and corridors opened, allowing species to colonize new territories. This dynamic view of biogeography provided a framework for understanding how life might persist and evolve under changing conditions. The same principles that allowed species to survive ice ages and continental drift might allow life to persist through the even greater changes that awaited in the future. The adaptability and resilience that Wallace observed in the species of the Malay archipelago might be universal features of life, capabilities that would serve living things well not just on Earth, but on any world where life might arise. The convergent patterns. As Wallace's understanding of biogeography deepened, he began to notice something remarkable. Similar environments, even when separated by vast distances, often produced similar forms of life. The concept of convergent evolution became central to his thinking. The idea that unrelated species could evolve similar traits when faced with similar environmental challenges. In the forests of the Malay archipelago, Wallace found birds that filled the same ecological roles as birds in other parts of the world, despite belonging to completely different evolutionary lineages. The hornbills of Southeast Asia occupied similar niches to the toucans of South America, both having evolved large, colorful bills for feeding on fruit. The pittas of Asia resembled the antbirds of the Amazon, both ground-dwelling species adapted for life in the forest understory. These convergent patterns revealed something profound about the relationship between environment and evolution. Despite the random nature of mutation and the contingent history of each lineage, evolution repeatedly produced similar solutions to similar problems. The constraints imposed by physics, chemistry, and ecology seemed to channel evolution towards certain forms, creating a hidden order beneath the apparent chaos of biological diversity. Wallace realized that these patterns of convergence provided a window into the fundamental principles governing life. If similar environments produce similar forms of life on Earth, then similar environments on other worlds might produce similar forms of life as well. The principles of convergent evolution might be universal, operating wherever life arose and diversified. The implications were staggering. If life existed in the oceans of Jupiter's moon Europa, it might evolve forms similar to Earth's marine life, constrained by the same physical laws and ecological principles. If life arose on a planet with dense atmosphere and low gravity, it might evolve forms of flight unknown on Earth, but governed by the same aerodynamic principles that shape terrestrial birds. Wallace's observations of convergent evolution also revealed the importance of ecological opportunity in shaping the course of evolution. On islands where certain types of animals were absent, other species often evolved to fill their ecological roles. In the absence of large predators, some birds evolved to enormous sizes and lost the ability to fly. In the absence of grazing mammals, some reptiles evolved to fill herbivorous niches. These patterns of adaptive radiation, where species diversified to fill available ecological niches, provided insights into how life might evolve on worlds with different starting conditions. A planet where vertebrates never evolved might see invertebrates diversify into roles filled by vertebrates on Earth. A world where plants never colonized land might see marine algae evolve into forms resembling terrestrial forests. The study of convergent evolution also revealed the limits of biological possibility. Despite the enormous diversity of life, certain forms appeared again and again, suggesting that there were optimal solutions to certain environmental challenges. The streamlined bodies of fast-swimming animals, the large ears of desert animals, the climbing adaptations of arboreal species. These forms appeared independently in many different lineages, suggesting that they represented fundamental solutions to environmental problems. Wallace began to understand that biogeography was not just about mapping the distribution of existing species, but about understanding the principles that govern the evolution of life itself. The patterns he observed in the Malay archipelago were manifestations of deeper laws that operated wherever life existed. These laws might be universal, governing the evolution of life not just on Earth, but on any world where life might arise. The recognition of convergent patterns also provided a framework for predicting how life might evolve under different conditions. If the principles of convergent evolution were universal, then it might be possible to predict the forms that life would take on worlds with different physical and chemical conditions. This predictive power would be crucial for the search for life beyond Earth, providing a guide for understanding what forms life might take on other worlds. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. The stepping stones of dispersal. Wallace's explorations revealed that the distribution of life was not simply a matter of suitable habitat, but depended critically on the pathways available for dispersal. The Malay archipelago, with its thousands of islands, provided a natural laboratory for understanding how species spread across fragmented landscapes. Some species were excellent dispersers, able to cross wide stretches of ocean to colonize distant islands. Others were poor dispersers, confined to single islands or small groups of closely spaced islands. The patterns of dispersal revealed much about the biology of different species. Birds, with their power of flight, were generally good dispersers, able to cross water barriers that stopped other animals. But even among birds, there were differences. Strong flyers, like raptors and seabirds, could cross vast distances, while weak flyers, like forest birds, were often confined to single islands or groups of closely connected islands. Marine currents played a crucial role in dispersal, carrying seeds, small animals, and even larger creatures across ocean barriers. Wallace observed that the direction and strength of currents influenced which species could colonize which islands. Islands downstream from major land masses often had more diverse biotas than those upstream, reflecting the one-way nature of oceanic dispersal. The concept of stepping stones became central to Wallace's understanding of biogeography. Species could often cross barriers that seemed insurmountable by using intermediate islands as stepping stones, colonizing each island in turn until they reached their final destination. The presence or absence of these stepping stones could determine whether a species could spread across a particular region. Wallace realized that the same principles that govern dispersal in the Malay archipelago might apply to dispersal across space. If life existed on multiple worlds, it might spread from world to world using asteroids, comets, or other celestial bodies as stepping stones. The concept of panspermia, the idea that life might spread throughout the universe, became more plausible when viewed through the lens of biogeography. The study of dispersal also revealed the importance of rare events in shaping biological distributions. Most dispersal events failed, with colonizing species unable to establish themselves in new environments. But occasionally, a few individuals would succeed in colonizing a new island, founding populations that could then diversify and adapt to their new home. These rare, successful dispersal events were the key to understanding how life spread across the planet. Wallace began to understand that the history of life was punctuated by these rare but crucial dispersal events. The colonization of new continents, the spread of life into new environments, the recovery of ecosystems after mass extinctions. All these processes depended on the ability of species to disperse across barriers and establish themselves in new areas. The implications for astrobiology were profound. If life could spread across the barriers of space, then the biological history of the universe might be shaped by similar patterns of dispersal and colonization. The first world to evolve life might serve as a source for colonizing other worlds, creating a pattern of biological distribution that reflected the pathways available for interplanetary dispersal. Wallace's insights into dispersal also revealed the fragility of biological distributions. Species that seemed secure in their current ranges might be vulnerable to the disruption of dispersal pathways. The destruction of stepping stone habitats, changes in ocean currents, or the emergence of new barriers could isolate populations and lead to extinction. This understanding of dispersal vulnerability became increasingly important as human activities began to alter the planet's dispersal pathways. The construction of dams, the clearing of forests, the pollution of oceans, all these activities could disrupt the natural processes of dispersal that had shaped the distribution of life over millions of years. The study of dispersal also provided insights into the potential for life to persist under changing conditions. Species with good dispersal abilities might be able to track changing climates, moving to new areas as their current habitats became unsuitable. Species with poor dispersal abilities might be more vulnerable to environmental change, unable to reach new suitable habitats as old ones disappeared. Wallace's work on dispersal revealed that biogeography was not just about understanding static patterns of distribution, but about understanding the dynamic processes that created and maintained these patterns. The same principles that govern dispersal in the Malay archipelago might govern the spread of life throughout the universe, providing a framework for understanding how life might be distributed across the cosmos. Now, close your eyes and imagine the cosmic dispersal of life. Picture how comets might carry biological material between worlds, how asteroid impacts might launch life from one planet to another, how the vast distances between stars might be crossed by hardy organisms in a slow dance of cosmic colonization. See how the principles Wallace discovered in earthly archipelagos might apply to the greatest archipelago of all, the scattered islands of worlds that orbit distant suns. The ecological tapestry. Wallace's understanding of biogeography deepened as he began to see species not as isolated entities, but as threads in a vast ecological tapestry. Each species was connected to others through webs of interaction, predation, competition, mutualism, parasitism that shaped their distributions and their evolutionary trajectories. The presence or absence of key species could determine whether entire ecological communities could establish themselves in new areas. In the forests of the Malay archipelago, Wallace observed intricate relationships between species that had evolved together over millions of years. Fig trees and their specialized wasp pollinators had co-evolved such specific relationships that each fig species could only be pollinated by its own unique wasp species. The distribution of figs was thus inseparable from the distribution of their pollinators, creating a complex pattern of interdependence that shaped the biogeography of entire forest ecosystems. These ecological relationships revealed new layers of complexity in biogeographic patterns. It was not enough for a species to be able to disperse to a new area and survive the physical conditions there. It also needed to find the ecological partners it depended on for survival. Herbivorous insects needed their specific host plants, flowering plants needed their pollinators, and predators needed their prey. The successful colonization of new areas required the establishment of entire ecological networks, not just individual species. Wallace began to understand that the distribution of ecological communities was often more constrained than the distribution of individual species. A forest ecosystem might be unable to establish itself in an area where the climate was suitable, but where key species were absent. Conversely, the presence of key species could facilitate the establishment of entire ecological communities, as the arrival of one species created opportunities for others. The concept of keystone species became important in Wallace's thinking. These were species that had disproportionate effects on their ecological communities, whose presence or absence could determine the fate of many other species. The loss of a keystone species could trigger cascading effects throughout an ecosystem, while the introduction of a keystone species could transform an entire biological community. Wallace realized that these ecological relationships added new dimensions to the biogeographic effects of barriers and corridors. A barrier that was permeable to individual species might be impermeable to entire ecological communities if key species could not cross it. Conversely, a corridor that allowed the movement of key species might facilitate the spread of entire ecosystems. The study of ecological relationships also revealed the importance of historical contingency in biogeography. The ecological communities that established themselves in different areas depended not just on current conditions, but on the order in which species arrived and the ecological interactions that developed. Two areas with identical physical conditions might develop very different ecological communities if they were colonized by different species, or if the same species arrived in different orders. These insights into ecological biogeography had profound implications for understanding how life might be distributed on other worlds. If life existed on multiple planets, the ecological relationships that developed on each world would be shaped by the unique history of colonization and evolution on that world. The same physical conditions might support very different forms of life depending on which species arrived first and what ecological relationships developed. Wallace's understanding of ecological tapestries also revealed the vulnerability of biological communities to disruption. The complex webs of interaction that had evolved over millions of years could be disrupted by the loss of key species or the introduction of new ones. The biogeographic patterns that had taken millennia to establish could be altered in decades by human activities. The concept of ecological restoration became important in Wallace's later thinking. If ecosystems were disrupted, they might be restored by reintroducing key species and reestablishing important ecological relationships. But such restoration required a deep understanding of the ecological principles that govern the assembly and maintenance of biological communities. Wallace's work on ecological biogeography provided a framework for understanding how life might be distributed not just in space, but in ecological space, the multidimensional space of ecological relationships and interactions. The same principles that govern the distribution of ecological communities on Earth might govern the distribution of life throughout the universe, providing insights into how complex biological systems might arise and persist on other worlds. The recognition of ecological relationships also provided new perspectives on the search for life beyond Earth. The detection of life on other worlds might require not just the identification of individual organisms, but the recognition of ecological patterns and relationships that indicated the presence of complex biological communities. The biogeographic principles that Wallace discovered might serve as a guide for understanding how such communities might be distributed across the varied landscapes of distant worlds. The universal principles. As Wallace's career progressed, he began to recognize that the patterns he had observed in the Malay archipelago were manifestations of universal principles that governed the distribution of life wherever it existed. These principles transcended the specific conditions of Earth, providing a framework for understanding how life might be distributed throughout the universe. The principle of environmental filtering emerged as one of the most fundamental of these universal laws. Every environment acted as a filter, selecting for organisms with the traits necessary to survive and reproduce under its specific conditions. This filtering process operated at multiple scales, from the immediate effects of temperature and humidity to the long-term effects of climate change and geological activity. Wallace realized that environmental filtering would operate on any world where life existed. The specific conditions of each planet would select for different traits, creating unique assemblages of organisms adapted to local conditions. But the underlying process would be the same. The environment would filter the available species, allowing some to persist while eliminating others. The principle of distance decay provided another universal framework for understanding biogeographic patterns. The similarity between biological communities decreased with increasing distance, reflecting the limitations of dispersal and the accumulation of environmental differences across space. This principle operated not just across the surface of Earth, but potentially across the vast distances of space itself. If life existed on multiple worlds, the principle of distance decay suggested that nearby worlds would have more similar forms of life than distant worlds. The biological communities of planets in the same solar system might share common ancestors, while those in different solar systems might be completely independent evolutionary experiments. The principle of island biogeography emerged from Wallace's observations of species-area relationships and the effects of isolation on biological diversity. Smaller, more isolated habitats supported fewer species than larger, better connected habitats. This principle applied not just to oceanic islands, but to any fragmented habitat, forest patches, mountaintops, desert oases. Wallace began to understand that planets themselves might function as islands in the cosmic ocean, with their biological diversity depending on their size, their degree of isolation, and their history of colonization. Larger planets might support more complex biological communities than smaller planets, while planets in dense stellar neighborhoods might have more diverse biotas than those in isolated regions of space. The principle of adaptive radiation provided insights into how life might diversify when colonizing new environments. When species encountered new ecological opportunities, they often diversified rapidly, evolving into forms adapted to different niches. This process had produced the spectacular diversity of life on Earth, from the finches of the Galapagos to the cichlid fish of the Great Lakes. Wallace realized that adaptive radiation would be a universal feature of life, operating wherever organisms encountered new ecological opportunities. The colonization of new planets might trigger spectacular bursts of evolutionary diversification as life adapted to the unique conditions of each world. The principle of convergent evolution suggested that similar environmental conditions would produce similar forms of life, regardless of their evolutionary history. This principle provided a framework for predicting what forms life might take on other worlds with known environmental conditions. Wallace began to understand that these universal principles might serve as a guide for exploring the biological universe. The search for life on other worlds could be informed by biogeographic theory, helping scientists understand where to look for life and what forms it might take. The recognition of universal principles also provided insights into the future of life on Earth. As human activities continued to alter the planet's environments, the same principles that had shaped the distribution of life in the past would continue to operate in the future. Understanding these principles would be crucial for predicting how life might respond to environmental change and for developing strategies for conservation and restoration. Wallace's work revealed that biogeography was not just a descriptive science, but a predictive one. The principles he discovered provided a framework for understanding how life might be distributed under different conditions, both on Earth and beyond. These principles might serve as a guide for humanity's expansion into space, helping us understand how life might be distributed across the galaxy and how we might establish sustainable biological communities on other worlds. Now, close your eyes and imagine these universal principles operating across the cosmos. Picture how environmental filtering might work on worlds with different atmospheres, how distance decay might operate across interstellar distances, how adaptive radiation might produce spectacular diversity on newly colonized planets. See how the principles Wallace discovered in earthly archipelagos might govern the distribution of life throughout the universe, connecting the smallest island to the vastest reaches of space. The cosmic archipelago. In the gentle twilight of understanding, Wallace's insights transcend the boundaries of Earth and extend into the infinite archipelago of space. Just as the Malay Islands dotted the azure seas of Earth, so do countless worlds drift through the cosmic ocean, each one a potential harbor for life's endless experiments. The principles that governed the distribution of butterflies and birds in tropical forests might someday guide humanity's understanding of how life spreads across the galaxy. The concept of the habitable zone, that narrow band around each star where liquid water might exist, becomes a cosmic analog to the climate zones that Wallace mapped on Earth. Just as tropical species could not survive in Arctic conditions, so life adapted to one type of star might struggle to survive around a different type of star. The red dwarf stars that burn for trillions of years might harbor forms of life adapted to their dim, steady radiance, while the brief, brilliant lives of massive stars might support only the most rapidly evolving organisms. The distances between stars, vast beyond earthly comprehension, create barriers to dispersal that dwarf the ocean channels Wallace studied. Yet the principles remain the same. Life might spread from star to star using comets and asteroids as stepping stones, just as it spread from island to island using ocean currents and floating debris. The timescales are different, measured in millions of years rather than seasons. But the underlying processes might be identical. Each planetary system becomes its own biogeographic province, shaped by the unique history of its formation and the specific characteristics of its central star. The arrangement of planets, the presence of asteroid belts, the dynamics of orbital resonances, all these factors might influence how life spreads and evolves within each system, creating patterns as distinctive as the biological signatures Wallace found in different island groups. The gas giant planets, with their complex systems of moons, become archipelagos within archipelagos. Jupiter's moons form their own biogeographic realm, with Europa's subsurface oceans, Io's volcanic landscapes, and Ganymede's ice-covered surface, each potentially harboring unique forms of life. The gravitational interactions between these moons, the tidal heating from Jupiter's immense gravity, the radiation environment created by the planet's magnetic field, all these factors might create biogeographic patterns as complex as those Wallace observed in the Malay archipelago. The concept of planetary refugia emerges as climate change and stellar evolution alter the habitability of different worlds. During periods of stellar instability, life might retreat to underground sanctuaries or deep ocean trenches, waiting out the harsh conditions before emerging to recolonize the surface. These refugia might preserve ancient forms of life, creating living fossils that persist across geological ages, just as the isolated islands of Earth preserved relic species that had vanished from the mainlands. The migration of planets themselves, as gravitational interactions alter their orbits over cosmic time, creates a dynamic biogeography that unfolds across billions of years. A world that begins in the outer reaches of a solar system might gradually spiral inward, its life forms adapting to increasing temperatures and changing radiation levels. Conversely, a planet ejected from its birth system might carry its biosphere into the cold darkness of interstellar space, where life might persist in geothermally heated environments beneath frozen surfaces. The galactic environment itself becomes a factor in cosmic biogeography. The spiral arms of galaxies, with their higher density of stars and more frequent supernovae, might create regions of elevated radiation that challenge the persistence of complex life. The galactic center, with its supermassive black hole and intense gravitational fields, might harbor forms of life adapted to extreme conditions. The outer reaches of galaxies, where stars are sparse and metals are rare, might support only the most efficient and minimalistic forms of life. The concept of biological corridors extends to the cosmic scale, as streams of ejected material from asteroid impacts create pathways for the transfer of life between worlds. These impact-generated streams might follow predictable trajectories through space, creating biological highways that connect distant worlds across the galaxy. The timing of these impacts, their intensity, and their direction might all influence the patterns of life's distribution across space. Wallace's insights into the role of historical contingency in biogeography take on new meaning when applied to the cosmic scale. The first world to evolve intelligence might play a role similar to a continental source, seeding nearby worlds with life and establishing patterns of biological distribution that persist across cosmic time. The order in which different worlds are colonized, the types of life that successfully make the journey between worlds, the ecological relationships that develop in each new environment, all these factors might create patterns of cosmic biogeography as complex and contingent as those Wallace observed on Earth. The search for extraterrestrial life becomes an exercise in cosmic biogeography, using the principles Wallace discovered to predict where life might be found and what forms it might take. The detection of life on one world might provide clues about the likelihood of finding life on nearby worlds, just as the discovery of a new species on one island might predict the presence of related species on neighboring islands. As consciousness drifts toward the realm of dreams, the patterns Wallace discovered in the tropical archipelagos of Earth expand to encompass the infinite archipelagos of space. The same principles that govern the distribution of life across the scattered islands of Southeast Asia might govern the distribution of life across the scattered worlds of the galaxy. In this cosmic perspective, every world becomes an island, every solar system an archipelago, every galaxy a vast ocean dotted with countless opportunities for life's endless creativity. The gentle rhythm of cosmic time, measured in the slow dance of planets around their stars, in the patient evolution of stellar populations, in the gradual enrichment of galaxies with the heavy elements necessary for life, becomes a lullaby that carries the mind into peaceful sleep. In this cosmic biogeography, the boundaries between Earth and space dissolve, revealing the fundamental unity of all life, wherever it might arise, whatever forms it might take, whatever worlds it might call home. The eternal return. In the deepest hours of night, when the world settles into its most profound stillness, Wallace's vision completes its circle, returning from the cosmic reaches of space to the intimate details of life on Earth. The principles that might govern the distribution of life throughout the universe are the same principles that governed the distribution of butterflies and birds in the forests of Borneo, the same principles that shaped the unique biological communities of each island in the Malay archipelago. The recognition of this fundamental unity provides a sense of peace and continuity that transcends the apparent chaos of existence. Every living thing, from the smallest bacterium to the most complex ecosystem, from the most isolated island to the most distant galaxy, participates in the same grand pattern of distribution and adaptation, dispersal and evolution that Wallace first glimpsed in the tropical islands of Southeast Asia. The boundaries that seem so important in daily life, the boundaries between species, between ecosystems, between Earth and space, dissolve in this deeper understanding. All life is connected through the invisible threads of biogeography, through the shared history of dispersal and adaptation that links every living thing to every other living thing across the vast expanses of space and time. Wallace's journey from the Amazon to the Malay archipelago, from the observation of individual species to the understanding of universal principles, becomes a metaphor for the journey of consciousness itself. Each insight builds upon previous insights. Each discovery reveals new layers of complexity and beauty. Each understanding opens new vistas of wonder and possibility. The patterns that Wallace discovered continue to unfold across the planet as species adapt to changing conditions, as new barriers arise and old ones disappear, as the endless dance of geography and biology continues its ancient rhythm. Climate change, habitat fragmentation, and species extinctions create new biogeographic patterns, while conservation efforts and ecological restoration create new opportunities for life to spread and diversify. The principles of biogeography provide a framework for understanding these changes, for predicting how life might respond to future conditions, for developing strategies that work with natural processes rather than against them. The wisdom that Wallace gained from his years of observation and reflection continues to guide humanity's relationship with the natural world, providing insights that are as relevant today as they were when he first articulated them more than a century ago. The search for life beyond Earth continues, guided by the biogeographic principles that Wallace discovered. Each new discovery, from the detection of organic molecules in interstellar space to the identification of potentially habitable exoplanets, adds another piece to the vast puzzle of life's distribution throughout the universe. The same curiosity that drove Wallace to explore the remote islands of Southeast Asia now drives humanity to explore the remote worlds of distant solar systems. The tools of exploration have changed, from butterfly nets and specimen jars to space telescopes and robotic probes, but the fundamental questions remain the same. Where does life exist? How does it spread? What factors determine its distribution? How does it adapt to different conditions? The principles that Wallace discovered in earthly archipelagos continue to guide the search for life in the cosmic archipelagos of space. As the night deepens and consciousness drifts toward sleep, the gentle rhythm of biogeographic processes continues its eternal dance. Species migrate along ancient pathways, adapt to changing conditions, and establish new populations in distant habitats. The invisible lines that Wallace first mapped in the Malay archipelago continue to shift and change, reflecting the dynamic nature of life's relationship with the Earth. In dreams, perhaps, the boundaries between self and world, between Earth and cosmos, between past and future, dissolve completely. In this state of unity, the patterns that Wallace discovered become not just scientific principles, but expressions of the fundamental interconnectedness of all existence. The distribution of life across space and time becomes a meditation on the nature of existence itself, a gentle reminder that every living thing is part of a vast, ongoing experiment in the art of being alive. The legacy of Alfred Russel Wallace lives on in every biogeographic study, in every conservation effort, in every moment of wonder at the complexity and beauty of life's distribution across the planet. His insights continue to guide humanity's understanding of life's patterns, providing a framework for appreciating the intricate relationships that connect every living thing to every other living thing across the vast tapestry of existence. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo beneath the stars. Now, close your eyes and let the gentle rhythm of biogeographic processes carry you into peaceful sleep. Feel the slow pulse of evolution, the patient work of adaptation, the endless creativity of life spreading across countless worlds. Rest in the knowledge that you are part of this vast pattern, connected to every other living thing through the invisible threads of biogeography. Let the wisdom of Wallace's discoveries guide you into dreams of infinite archipelagos where life continues its eternal dance of distribution and adaptation beneath the gentle light of distant stars. In the quietest moments before sleep, when the mind releases its grip on the details of daily existence, the patterns that Wallace discovered reveal their deepest meaning. They speak not just of the distribution of life across space, but of the distribution of consciousness itself, of the way awareness spreads through the universe like seeds on the wind, finding new homes in the infinite gardens of possibility. The biogeography of consciousness, like the biogeography of life, follows patterns of dispersal and adaptation, of barriers and corridors, of islands and mainlands. Each mind becomes an island of awareness in the vast ocean of existence, connected to other minds through invisible currents of thought and feeling, part of a larger pattern that extends across species, across worlds, across the entire cosmos. Wallace's journey from the foggy shores of England to the tropical islands of Southeast Asia becomes a metaphor for the journey of awareness itself, always seeking new territories to explore, new patterns to discover, new connections to make. The same spirit of curiosity and wonder that drove him to collect specimens and map distributions continues to drive the human quest for understanding, the endless search for patterns that reveal the hidden order beneath the apparent chaos of existence. As sleep approaches, the boundaries between observer and observed, between the one who maps and the territory being mapped, begin to dissolve. The patterns become not just objects of study, but aspects of the studying itself. Not just phenomena to be understood, but expressions of the understanding that seeks to comprehend them. In this state of unity, the biogeography of the external world merges with the biogeography of consciousness, revealing the fundamental interconnectedness of all existence. The gentle rhythm of breathing becomes synchronized with the gentle rhythm of biogeographic processes, each breath a small migration, each heartbeat a moment of adaptation, each thought a dispersal event in the vast archipelago of consciousness. The boundaries between self and world, between mind and nature, between earth and cosmos, dissolve in the peaceful recognition that all existence participates in the same fundamental patterns of distribution and relationship. In the deepest rest, where dreams merge with dreamless sleep, the patterns that Wallace discovered continue their eternal dance. Life spreads across countless worlds. Consciousness explores infinite territories, and the great work of existence continues its patient unfolding across the vast expanses of space and time. The biogeography of being itself becomes a lullaby that carries all things into the gentle embrace of cosmic unity. The last conscious thought, before sleep claims its gentle victory, might be a recognition of the profound gift that Wallace gave to humanity. Not just an understanding of how life is distributed across the planet, but a framework for understanding how consciousness itself might be distributed across the universe. In this final recognition, the journey from the particular to the universal, from the local to the cosmic, from the individual to the infinite, completes its circle, and all existence rests in the peaceful knowledge of its fundamental unity. Sleep comes at last, carrying with it the gentle patterns that Wallace discovered, the invisible lines that connect all living things, the endless creativity of existence expressing itself through the distribution of life across the infinite archipelagos of space and time. In dreams, perhaps, the boundaries between worlds dissolve completely, and consciousness travels freely through the vast territories of possibility, following the ancient pathways of biogeographic dispersal into the infinite gardens of the cosmos. The rhythm of universal processes continues its eternal dance, carrying all things toward rest, toward renewal, toward the endless creativity of existence, expressing itself through new patterns of distribution and relationship. In this gentle rhythm, the wisdom of Wallace's discoveries finds its deepest expression, not as scientific principles, but as expressions of the fundamental love that connects all existence, the infinite compassion that guides the distribution of life across the vast territories of being, and in the quietest moments of deepest sleep, when all boundaries have dissolved and all patterns have merged into the unified field of existence, the biogeography of the universe reveals its ultimate secret, that all distribution is the distribution of love. All adaptation is the adaptation of consciousness. All dispersal is the dispersal of infinite possibility across the endless archipelagos of dreams.